For years, stories about sugar in space have floated around astronomy headlines, but in most cases, that phrase came with an important catch. The molecule often being discussed was glycolaldehyde, which is certainly interesting for prebiotic chemistry, but not a sugar in the narrow sense. In 2026, researchers reported something more ambitious. Erythrulose, in the interstellar cloud, G plus 0.693, 0.027, presented as the first true sugar directly detected in the interstellar medium. If that identification holds up, it marks a real threshold. It would suggest that chemistry between the stars has moved, at least in one confirmed case, from sugar-like precursors to an actual sugar. That does not prove life-related chemistry is easy or inevitable, but it would show that interstellar space can host more chemically advanced processes than had previously been confirmed directly. The cloud at the center of this story, G plus 0.693, Chi01027, sits near the galactic center and has become famous for being chemically rich. It is not a calm, pristine nursery. It is a place shaped by shocks, radiation, and turbulence, conditions often described as driving chemistry forward. In other words, this is exactly the kind of environment where researchers would hope to find unusual and complex molecules if nature can assemble them before planets even form. Now, no one scooped up a sample of this cloud and ran it through a lab instrument. The claim is spectroscopic. Radio telescopes search for molecules by detecting characteristic rotational transitions. A molecule can tumble and rotate only in specific ways, and those motions interact with radio wavelengths to create a kind of spectral fingerprint. If enough of the expected lines appear where they should, and with the right broader pattern, scientists can argue that a particular molecule is present in the gas. In this case, the strongest supporting evidence is that researchers reported 12 matching sets of spectral lines attributed to erythrulose's expected rotational transitions. That is the core of the claim. And according to the published analysis, the case does not rest only on getting the frequencies roughly right. The reported identification also depends on the pattern of lines, their relative intensities, a plausible excitation temperature, and comparisons against known molecules that might otherwise explain the signals. Taken together, the analysis argues for high statistical confidence. That is the pro-detection case as summarized in the narration behind this brief. And it matters to be clear about the source criticism here. The evidence comes from a published analysis making that argument. What we have is the narration's summary of that analysis, not the direct underlying data, and not a fresh re-evaluation line by line. So the claim may be convincing, but it is not something we should treat as permanently settled just because it was published. And there is a serious reason for caution. G plus 0.693 to 0.027 is spectrally crowded. In a cloud loaded with molecules, many signals can overlap. This is what astronomers call line confusion, and it is the strongest counterpoint in the story. In such an environment, overlapping features can imitate the signature of a molecule that is not actually there, or at least make the case less secure than it first appears. The researchers may have built a strong identification, but overlaps cannot be ruled out completely. There are also narrower, open questions. Were alternative identifications for some of the lines excluded well enough? In a source this busy, that is always the hard part. And then there is the chemistry itself. The proposed formation routes are plausible, but they are not experimentally pinned down in full detail. So even if the spectral assignment is right, the exact path by which erythrulose formed in that cloud remains less certain. Still, the reason this claim has drawn so much attention is that it fits into a broader picture of interstellar chemistry that has been building for years. The favored mechanism here is chemistry on ice-coated dust grains. In cold molecular clouds, tiny dust grains accumulate frozen layers of simple molecules. On those icy surfaces, ultraviolet light, radiation, reactive radicals, and gradual warming can drive reactions toward more complex compounds. Instead of gas-phase chemistry doing all the work, the ices act like microscopic reaction platforms. For erythrulose specifically, the proposal is stepwise reactions of smaller precursors on those icy grain surfaces. Over time, those reactions may assemble a more complex carbon-bearing structure. Later, heating or shocks can release the resulting molecule from the ice back into the gas. Once it is in the gas phase, telescopes have a chance to detect its rotational transitions. That scenario makes sense in a cloud like G plus 0.69300.027, where shocks and energetic processing are already part of the environment. What does that mean for astrobiology? First, what it does not mean. Researchers did not find ribose, and they did not find deoxyribose. Erythrulose is not the sugar in RNA and not the sugar in DNA. So this is not a discovery of genetic material sugars drifting through interstellar space, and it does not suddenly solve the origin of life. The more limited implication is still important. If a true sugar exists in the interstellar medium, then young planetary systems may not begin from zero chemically. Some intermediates, or at least some of the complexity that leads toward them, could be inherited from molecular clouds and carried forward through later stages of star and planet formation. That would strengthen a view in which prebiotic chemistry begins before planets are fully assembled, not only after. There is also a tempting question about chirality, the handedness of molecules, which matters deeply in biology. But this detection does not solve that. It does not show any pre-existing biological preference, and it doesn't explain why life uses one-handedness over another. At most, it broadens the chemical setting in which such questions might one day be asked. It says the stage may have been richer, earlier, and more distributed than once assumed, not that the central mystery has been answered. The chronology matters too. Sugars and related compounds had already been found in meteorites and in material from Bennu. Those are real and important discoveries, but they belong to solar system solids. If erythrulose really has been identified in an interstellar cloud, then sugar chemistry gets pushed earlier and farther outward, into the molecular cloud phase before the solar system-style solid bodies we can physically sample. That would be a meaningful expansion of where we know this chemistry can happen. So where does that leave the headline claim, the first true sugar in the interstellar medium? It is a strong claim, and right now it should wear a caution label. The published analysis reportedly presents a strong case, including 12 matching line sets, a fitting pattern of relative intensities, a plausible excitation temperature, and comparisons against known species. That is enough to make erythrulose a serious and exciting candidate. But not enough to close the case forever. Further observations are needed. Better laboratory data would help. Independent confirmation matters, especially in a spectrally crowded source where line confusion remains a real possibility. Some alternative identifications may need to be challenged more rigorously, and the proposed formation chemistry still needs fuller experimental support. In other words, this is exactly the kind of result that can be both impressive and provisional at the same time. The most responsible reading is not, "Scientists have proven life's ingredients were waiting in space," and not, "This is just another overhyped molecule that means nothing." It is something more interesting in between. Erythrulose appears to be a strong candidate for the first true sugar directly detected in interstellar space. If that identification survives further testing, it would support the view that molecular clouds are active sites of preplanetary prebiotic chemistry, places where complexity can emerge well before worlds like ours take shape. And if later work weakens the claim, that will still tell us something important about how careful we have to be when interpreting crowded astronomical spectra. Either way, this is frontier science doing what frontier science does, pushing into a difficult region, making a bold but testable claim, and inviting the community to try to confirm it or break it. For now, the bottom line is clear. Erythrulose in G plus 0.693.0.027 is a strong but still provisional candidate for the first true interstellar sugar. It hints that the chemistry between the stars may be more advanced than we had directly confirmed, while leaving key tests outstanding. If you enjoyed this, subscribe, enable notifications, and tell us in the comments what topic we should explore next.